Okay, students, I'm going to try to do this on my phone so that I can actually write out. We'll see how this works. I'll try not to make you sick by moving it around too much. Please try this first on your own. Pause this video, do this example, same way as the previous one, and then we'll do this together. So what you might want to start with is, let's see, I'm going to write out, first we're going to write for practice 17.15, so we know which example we're doing. What it tells us is we have 250 mils of 0.0117 molar nickel chloride. So first, we have two beakers. Okay, here's one beaker, here's another beaker. One beaker contains 125 milliliters of 0.0117 molar nickel, right? Because we only care about the nickel. We don't care about the chlorine. Our other beaker has 175 milliliters of 0.25 molar NH3, right? So I'm just following along what it says, what we have. What's going to happen here, these two are going to mix together, right, to give us some equilibrium. So we're going to mix these two together. So in our new beaker, once we've mixed them together, we had 125 mils and 175 mils. So now we have 300 mils. In our beaker, we now have nickel 2 plus, but we don't know the concentration, right? Because it was 0.0117, but we diluted it because we added this ammonia solution. So now this is going to be less than 0.00117. And this ammonia concentration is also going to be less than what we started with. So we don't know that concentration either. So we'll have to figure those out before we can do our ice table. So let's go ahead and write out what our expression is. So we're going to have nickel, right? We're taking nickel, aqueous. We're adding it to ammonia, which is also aqueous. What are we going to get? Well, we're going to get some nickel ammonia complex, right? But what exactly is it going to be? How many ammonias are we going to have? I don't know. So what we're going to do is we're going to look at our chart. So we need to find on our chart where our nickel ammonia is. It looks like we're going to have 6 of them. There is no easy way for us to tell this. We would have to look at this chart to figure out that there's 6 of them. And they gave us a KF of 2.0 times 10 to the 8th. So I'm going to come back here and I'm going to write, here we're going to have a 6. This is a 2 plus. It's aqueous. And our KF is 2.0 times 10 to the 8th. So now we have our expression, right? Our nickel is going to add with our ammonia. So our nickel and our ammonia are going to add together. Down here, we'll have some initial concentrations of each. Once the reaction occurs, we'll have some concentration of our nickel ammonia complex ion. And we have the KF value. So initially, we need to find what these two concentrations are. So let's do our nickel first. So our nickel 2 plus initially, concentration. Well, let's see. We started with 125 mils of 0.0117 molar nickel. So let's find how many moles we have first. So if we started with 125 mils, right, 1,000 milliliters are in 1 liter, so our milliliters cancel. Our concentration is 0.0117 moles per 1 liter, so our liters cancel. So we're left with moles of nickel, right? So we should get 0.00146 moles of nickel. That's moles. We want concentration, right? So we're going to divide it by our total volume. So we're going to divide it by 0.3 liters, right? Because that's 300 milliliters. So you should get 0.004875 molar nickel. So that's our concentration of nickel initially, right, in this beaker. So I can write that here if I want. I'm going to go ahead and put that in scientific notation so I know this concentration now. Let me go ahead and do that with the ammonia. So our ammonia, we're trying to find the initial concentration. We started with 175 mils of it, right up here, and here's the concentration. So I'll convert milliliters to liters. Right, milliliters canceled. 0.25 moles per 1 liter. Liters cancel, I'm left with moles. So my mole should be 0.04375 moles of ammonia per, once again, we're at 300 milliliters or 0.3 liters. So we should get 0.1458 molar of ammonia. So I'm going to put that up here, 1458 molar. So now we know our initial concentrations of both. So now we can do our ice table. So we have our let's start with our nickel. So we have our nickel plus our ammonia is going to give us, it's only going to go one way, our nickel ammonia complex, right? Technically that means we need 6 here. Oops, didn't put that up there. Let's put that 6 in there. Because we had 6 ammonias here, we need 6 ammonias there. So our ice table, initially our nickel concentration we said was 4.875 times 10 to the negative third. Our ammonia concentration is 0.1458 molar, and then we don't have any of our complex yet because all we have, we mix these 2 beakers together. Initially, all we have are nickel and ammonia, so those are down here. We solve those concentrations. That's still 0. So here's the thing where it gets tricky. Remember, most of this nickel is going to be used up, but not all of it. So we're going to say approximately it's going to decrease by 4.875 times 10 to the negative third. Even though this should give us 0, right? We're going to say that since it's approximately, it's going to give us X. That's what we're solving for. We want the nickel concentration at equilibrium. That's what it's asking for. This one is going to also approximately decrease by, well, we got a 6 here, so 6 times, going to decrease by 4.875 times 10 to the negative third. If we do that math, we see that it comes out to be 0.11655. And then this one over here is going to increase by, once again, approximately 4.875 times 10 to the negative third. So it's going to be 4.875 times 10 to the negative third. So now we have our equilibrium of all of our different components. We can write our KF expression. So the KF is going to be, once again, it's going to be our products over our reactants. And then we can plug our numbers in. So we actually do have a KF value. So our KF, remember, was, where is it? 2 times 10 to the 8th. So 2.0 times 10 to the 8th equals 4.875 times 10 to the negative third over, let's see, that's